Hello, my name is Kaley Chung.
Hi, I'm Sude.
Hi, I'm Pranav Battini.
Hello, my name is Navaneeth Dontuboyina, and today with our mentors Professor Mut Pilanci, Rajeshri Saha, Zachary Shah, Indu Subramaniam, and Feng Zhao Zhang, we are presenting our project, Bridging the Gap in Generative AI for Audio Generation.
Generative AI has come a long way in recent years, a really long way. Programs like ChatGPT, DALL-E, they're becoming incredibly popular worldwide, and they all use something called diffusion models to help them achieve their success. But while all of these products are great, they all focus on language processing or image generation. We have to focus on audio generation because the current market doesn't have that. It's just not that popular. And the uses for it are immense. With the technology from audio generation, we can generate new datasets. We can improve on existing datasets. We can improve the performance of AI models. The list goes on, and we'll be detailing them in further slides. But for now, our project focuses on music generation, specifically similar projects to what the Kaley Lab is working on.
So, our project seeks to fill the gap of AI's ability to generate auditory media through refining a modifiable model. And this can be used for commercial use with implications of refusion and diffusion libraries and expanding or improving model training. And then for our solution, we use Jupyter Notebook's Anaconda or Google Colab's and Zachary Shaw's rough to pick model.
In our first milestone, we experimented with Zachary Shaw's Riff-Pix-to-Pix model, which basically paints in a vocal melody based on a text prompt. So this model first converts the audio to spectrograms, which basically is an image representation of an audio clip, and then generates a unique vocal for the provided background track using the already trained model. So to give an example, down below we can see the two spectrograms I generated. One is the original and the other is the edited sample, and we can clearly see the difference between the two. So let me play them real quick. This is the original. And this is the edited one.
In our second phase, or milestone, if you will, of our project, we used two Jupyter notebooks, Generate Splices and Splice Together. Generate Splices, quite simply, created splices from Zachary Shaw's Riff Pix-to-Pix and CNET models. And Splice Together fixed the limitation that Zachary Shaw's models could only generate 5-second snippets, and by using the Jupyter Notebook Splice Together, we were able to merge multiple snippets generated from the same prompt into a smooth, cohesive audio file using smoothing and fading techniques. And by generating now longer snippets of audio, we can now apply this audio to a large variety of real-world examples. Moving on, the third milestone in our project was where we created a new dataset on top of what Zachary Shaw had originally created in order to retrain our AI model to improve its generative AI performance. And we did this with two main technologies: Splitter, an AI that separates an audio file into its individual components, such as vocals, piano, bass, etc., and Librosa, a Python library that allows us to easily mix and match these components of an audio file to create new mixtures, such as just pieces, vocals, and drums, or pieces, vocals, drums, and bass, etc., in order to augment our dataset by using these additional files in order to expand what the model has to reference from during its training. And as it's a diffusion model, the more data that the model has to learn from, the better its output it's gonna be.
To dig a little deeper into Splitter, Splitter splits an audio file into its stems, or as we can call it, its components. These components include the vocals, piano, bass, drums, and other, which is the rest of the audio clip without the ones I mentioned. So to give an example, here's a short clip of jazz. It's bass, its drums, and what we call the other.
Labrosa, as we stated before, is a Python library that can be used to mix two different audio files together, provided they have the same sampling rate. In this project, we're using this tool to create different iterations of the original audio file by combining its stem components. As you can see on the top right in this block of code, it is combining the vocal stem, piano stem, and the drum stem to create an audio file that isolates these components from the other parts. Now that we have an array of these combinations, we will be able to filter them because most of the time the original audio file will not include all the 5 output stems Splitter is looking for. Thus, Splitter will sometimes hallucinate these components from the audio file, and Labrosa will combine these hallucinations. This will eventually give faulty results when we train our model later. Thus, we will have to go through the original description of the audio file from Incompetech and remove combinations which are inaccurate or rename them. For further improvements, we should make a script that stores the descriptions of each audio files in a list and iterates through the combinations, thus cleaning them up.
Using Labosa, we can mix 2 or more auditory wave files into one. So Labosa is a Python package that can overlay different tracks. So here are the key steps. 1, we load the auditory files using Labosa. 2, we check if the sample rates match. 3, we mix the 2 signals by adding. 4, we normalize the combined signals to avoid clipping. And 5th, we extort the mixed audio. And here is the code that we use to mix 2 audios. And as you can see here, there are 3 songs. So there's Mr. Gloomy, the original song, Mrs. Delicate, the original song, and then the third will be the mixed audio.
For our dataset documentation, we will have to create a CSV file to store the original file name, the edit prompt, and then the edited file name, so we have a way our model can go through our dataset. The edited prompt is actually generated by placing an original edit prompt into an NLP model and then generating a bunch of prompts rephrased from that original sentence. Thus, when our model will be trained to deal with different ambiguous and varying prompts, as this is a key aspect of our project.
Let's summarize what we've achieved in our project thus far. In our milestone 1, we created 5-second audio snippets and then used a prompt to add vocals to it. You can see our figure 2 is an example for this. We had background audio, and then in figure 3, we added the vocals to it, and you can see how that changes the spectrogram. That's great, but you don't really have much use for 5-second clips. That's why in our milestone 2, we made them longer. We stitched different splices together and essentially made a longer, more usable piece of music. And that means our data and our general outputs don't have to be limited to just music. We can focus on realistic data for autonomous driving, for really any computer vision model. Like, the list goes on in what our impact could potentially be. Furthermore, working with the Kaley Lab, we can continue to add more seamless transitions to their different audio frames. In our milestone 3, if we train our model with our newly augmented dataset, it would in theory perform much better because it has a more improved understanding of how different components of music kind of work together, and then it can use that understanding to cohesively kind of link everything, stack all the music together to create a beautiful piece of art. Furthermore, we have an increased reference point to draw from because of our efforts with Splitter and Labrosa.
Thank you for listening to our presentation.